In question 48, it says a model rocket is launched straight upwards with an initial speed of 50 meters per second. It accelerates with constant upward acceleration of 2 meters per second squared until its engines stop at an altitude of 150 meters. It want to know, A, at what is the maximum height that is reached by the rocket? We also want to know, B, how long after liftoff does the rocket reach its maximum height? And then lastly, part C, we want to know how long it is in the air. This is an example of a segmented motion problem. Now, it's segmented between two different one concept, but applied in different ways. This is a free fall acceleration problem and a constant acceleration problem. Okay, let me explain. To do this, let's break down this into the segments of motion. The first segment would be speeding up. Okay, and I'm talking about with the rocket engine. The rocket engine is causing the rocket to speed up as it goes up. So we're talking positive constant acceleration. Now, if that's the case, we list our variables. Instead of x, we use y, so y and y naught, v and v naught. We're going to use the a because this is not acceleration due to gravity. Okay, this is acceleration due to the rocket engine. So a is still the 2 meters per second squared given in the problem. And then t is t. So that's the first step in this problem, is the speeding up due to the rocket engines. Then what happens after a certain point is the rocket engine shut off, and this becomes a free fall acceleration problem now. So we can call this free fall acceleration to the highest point. And then lastly, on the way down, we would have free fall acceleration from the high point all the way back down to the ground. So these are our three basic parts of the motion. Now, these ones here, free fall to the highest point and free fall from the highest point, because once the rocket engine shut off, then the rocket accelerates due to gravity. It begins to slow down as it reaches its highest point because gravity pulls on it, and it begins to speed up from the highest point, again, because gravity pulls on it. However, this is where we can change this into a negative g and account for the 10 meters per second squared, because again, it's gravity's force that's causing the acceleration. Again, please notice the difference. In part 1, the rocket engine is causing the acceleration. In part 2 and 3, Earth's gravity is causing the acceleration. Okay, the variables are still the same nonetheless, and the concept is still constant acceleration. Okay, just due to what force is really what's talking about here. Now in step 1, let's go back and read the initial part of the problem. We are told that the rocket accelerates with an initial speed. So we can go back to this and we make this v naught equals 50 meters per second. Now, what we know, and if we draw a small sketch of this, here's what we can see. Here's the ground. We know the rocket takes off straight upwards. Okay, and it's got positive acceleration of 2 meters per second squared until it reaches this point right here. That point would be 150 meters off the ground. Then what it begins to do is it begins to slow down because gravity is accelerating it, and it's going to stop when it reaches the highest point, and then it's going to come back down to the ground. This is segment 1, right here. This is motion segment 2, slowing down on the way up. This is motion segment 3, on the way back down. So it helps to see it in a picture form so we can identify what parts goes which part of the motion. So I don't know the velocity at the end of when the engine shut off. I'm going to call that V1. So that's a question mark. The initial position of the rocket is on the ground, so 0. We know that Y is 150 because that's when the engine shuts off. This is the position. When the engine shuts off. And the time, we do not know the time, so the time is unknown to us. Gotta move this picture down a little bit more. In the second part of the problem, we don't know much either, but here's what we will be able to find out. The velocity, whatever velocity we find out right here, that's going to be the same as the initial velocities when the engine shuts off. Now here's what we do know about the second part. This final velocity is the velocity at the top. It's the velocity at the highest point. We know the velocity at the highest point has to be 0 because the rocket has to turn around at its highest point. We know that the position where it leaves off, where the engine shut off, is the initial position when the engine shuts off and it starts slowing down to its highest point, meaning Y naught here is 150. We don't know how high it gets. We have to find that out. And time we don't know. And then lastly, for part 3, we know we're coming down from the highest point, so if we treat the beginning of the problem as the highest point, then we know that this speed is going to be 0. We know that whatever our highest point is going to be our initial position, and we know we're going to end up on the ground, so the final position is 0. And again, we don't know the time. So remember, in a segmented motion problem, the position where one segment leaves off is the same position where another segment begins. The velocity where one segment ends is the continuing velocity of the next segment. Velocity and position continue between the segments. Okay, now let's look back at what we're trying to find. Part A, we want to know the maximum height reached by the rocket. Well, to find maximum height, we need to basically add y1 and y2. So part A, we want to know what is called y max. Y max would be y1 plus y2. Now y1 we already know is 150 meters, plus we need to find y2. Looking at the information we're given here, since I don't have time, I'm thinking about an equation that involves anything but time. The third equation is the only one that does not have time in it. V squared equals V naught squared minus 2g y minus y naught. V is 0. And if I take this entire term here and I add it over to the left side, I get 2g times the quantity of y minus y naught is equal to V naught squared. Then we can go ahead and divide the 2g both sides, and we get y minus y naught equals V naught squared over 2g. And lastly, we can add this y naught term over here. And we get y2 is equal to V naught squared over 2g plus y naught. Now, since we're already adding the plus y naught, we don't need to worry about doing this because y max is essentially going to be y2. Plugging in, y2, which is the same thing as y max, is equal to 50 squared over 2 times 10 plus 150. Well, 50 squared is 2,500 over 20, and then we need to add the 150 to it. And we get about 305 meters is how high the rocket will go. Okay, now part B is asking for how long after liftoff does it take to reach maximum height. So in other words, we want to know time going up. Time going up would be time for segment 1 plus time for segment 2. So look at your picture here. The time for this segment, which would be time 1, plus the time for that segment, which would be time 2. If we add them together, we'll get the total time after liftoff until it reaches its maximum height. We don't know either of those times, so we need to find them. So for segment 1, I can use the following. I can find the speed after the engine shut off. V squared equals V naught squared minus 2g times y minus y naught. Well, V would be equal to the square root of 50 squared minus 2 times 10 and then 305 minus 150. I'm sorry, for segment 1, we were accelerating due to the rocket engine, not due to gravity. So that would make this plus, there we go. Sorry about that. If we add the 2 times the 10 times the quantity of 305 minus 150, we'll get about a velocity of 55.7 meters per second. Now, using this information, we can use the first equation with that as the initial velocity and 50 meters per second as the initial velocity and 55.7 as the final, and we can solve for the time for segment 1. So let's do that. First thing I'm going to do is I'm going to add the GT over to this side, and I'm going to subtract the V over to this side, essentially swap those terms. And I get GT equals V naught minus V. Divide out the G. Let me see. Oh, silly me. I made the same goof. Plus AT. So I will want to subtract V naught both sides. And V minus V naught equals AT. T would be equal to V minus V naught over A. So time for segment 1 would be equal to 55.7 minus 50 over 2, which comes out roughly to about 2.85 seconds. That's not the answer, that's just the time for segment 1. Then if we do segment 2, we can use this equation here to find the time it takes to get up to the top. Why can we use this? Because we know the speed at the top is 0. 0 equals v naught minus gt2. I'm going to add this gt term over to the left, and I get gt2 equals v naught. Dividing both sides by g, t2 is equal to 50 over 5.7 over 10, which is 5.57 seconds. Okay, so just a point of clarification. This is V naught, but V naught for segment 2. So if we look back at segment 2, the initial speed of segment 2 is the final speed that it gets to. So the 55.7 meters per second that we found right here is the speed when the engine shut off. So it's also the initial speed for segment 2 when the rocket is slowing down due to gravity. And then lastly, we want to know in part C, my mistake, time going up would be time 1 plus time 2, which would be 2.85 seconds plus 5.57 seconds, or 8.42 seconds. So it takes 8.42 seconds to go upward. Now for part C, we want to know the time it takes to go down. Scratch that, we want to know the time it takes to be in the air. So time in the air would be time up plus time down. Now if the rocket were solely under the influence of gravity the whole time, then time up equals time down. But that's not the case here, because the rocket accelerated because of its own rocket engine up to a certain point, and then accelerated because of gravity the rest of the way. That makes this very asymmetrical with respect to time. So we basically have to figure it out by finding time up, time down, and then add them together. Well, if we take a look at the rocket coming back down from its highest point, okay, and then we can even go so far as to list our variables all over again just for a point of clarification. Y naught is the initial starting point, or the max height, of 305 meters. Y is the bottom level the rocket will get to on the ground, that's 0. The final velocity, about when it reaches the ground, I don't know it. The initial velocity is 0 because that's the velocity at the top. The acceleration due to gravity is 10. And time is what we're looking for. So, since I know both values of y, v naught, and a, it makes sense that we can use the second equation. Cancel things, such as the lowest position and v naught t. 0 equals v naught minus 1/2 gt squared. I'm going to go ahead and add this quantity over to the left-hand side, and we get 1/2 gt squared equals y naught. Solving for t, I'm going to multiply by 2. When I rewrite it, I get gt squared equals 2y naught. Divide by g. T squared equals 2y naught over g. Last step, square root. T, and this would be T3 on the way down, is equal to 2 times the height of 305 over g, which is 10. Plugging that in, we get roughly about 7.81 seconds. Therefore, the total time in the air would be time up plus time down. Time up we found to be 8.42 seconds plus time down 7.81 seconds and let's see, 8. And we get roughly about 16.3 seconds for total time in the air. Tough problem. This is a tough problem, but this is an example of a segmented motion problem in which it really helps you to not only chart up the information, but also chart up the picture into the different segments of motion.